today in this video lecture we will discuss one more mathematical operation which is performed by the operational amplifier, and that is the OPAMP as a differentiator. Already we have discussed one application of the OPAMP as a differential amplifier. Remember, the differential amplifier is amplifying the difference between the two input voltage, that is the V1 minus V2. Differentiator circuit is differentiating your input voltage. So output voltage is proportional to the differentiation of the input voltage. We have also discussed the integrator circuit. In the integrator, already you know, in the feedback part, the capacitor was connected, and at the input part, a resistance was connected. Here, if we interchange the position of the resistance and the capacitor, then the circuit will work as a differentiator. Now let us see what is the output voltage in this case. Here, for the analysis, we apply the concept of a virtual ground. Now what is a virtual ground? Here already you can see the non-inverting terminal is connected to the ground, means this potential is a 0 volt. Now here we consider the ideal operational amplifier. Ideal operational amplifier means what? The input resistance of the OPAMP is very high and the input current to the operational amplifier is zero. So as a result, here if we see the potential at this point will be also a 0. So whatever the current due to this input voltage, whatever the current I is flowing, the same current will also flow through this resistance Rf. Correct? Now we apply a Ohm's law at the input part. So what will be the expression for the current at the input, and what will be the expression for the current at the output? So let us say the current in the output part circuit, we can write I is equal to V by R. V means what? Potential difference across the resistance. Potential at this point is VA and the potential at this point is VO. Therefore we can write the VA minus VO divided by resistance RF. But the VA is 0. VA is 0, and therefore we can write this current I equal to minus VO by RF. Okay? Now we will calculate the current at the input part. Current at input circuit, and this current we can write as, basically we know that the current at the input part we have the capacitor, so in terms of the capacitor we have to write the current. So we know that the I is given by a dq by dt, rate of change of charge across the capacitor. Now what is Q? What is Q? That is the C into V. Here my capacitor is C1, so we will write the C1 into V. V is the voltage across the capacitor. Now what is the voltage across the capacitor? That is the VI and difference of the VI and VO. This is a VI and this is VO. So here we will write this is minus C1 d by dt VI minus VA. But the VA is equal to 0, and therefore minus C1 into dVi by dt, because the VA is equal to 0. So this is the current at the input part. So you can compare this equation number 1 and equation number 2. So we can write that from the equation 1 and equation 2, that is minus VO by RF is equal to minus C1 dVI by dt. Sorry, here you cannot have a minus sign because it is C1 into V is there. So it's my mistake. So negative sign will not be there. So it is C1 into dVI by dt. And therefore, the output voltage of this differentiator is given by minus RF into C1 dVI by dt. Here, RF into C1, it is known as a time constant. Okay? And you can see that this output voltage is proportional to the dVi by dt, that is the differentiation of the input signal. Now let us see, if we apply the different types of the waveform at the input like a sine wave, square wave, step wave or a triangle wave, what type of the waveform will be present in the output of the differentiator circuit. We apply a sine wave signal. Suppose this sine wave is given by V is equal to, or you can say the Vi is equal to Vm sine omega t. Then what is the output voltage? That is the differentiation of the input. So the output voltage is given as minus Rf into C1 d by dt, and my input voltage is Vm sine omega t. So this is equal to, we can write minus Rf C1, and Vm is a constant, and differentiation of omega t will be omega, and then differentiation of the sine omega t is going to be a cos omega t. This is the output voltage. Now to understand this shape of the signal, here we consider the RFC1 is, let us say, unity. Means here suppose this my RF is equal to a 1 mega ohm, C1 is 1 microfarad. So what is my time constant? RF into C1 is going to be a 1 second. Correct? So the output voltage of the differentiator will be minus Vm into omega cos omega t. So input is a sine wave, then you can see the output is going to be a cos wave. So here if I will draw the waveform, let us say we have this time axis, and what is my maximum input voltage? That is the Vm. This one is 0, this is t by 2, and this is your t. Somewhere here we have t by 4. Okay. So for the different time, here if we calculate the output voltage, that you can see from this, that t is equal to 0, output voltage is equal to minus Vm into omega, and the cos 0 will be there. So here it is going to be a minus Vm omega. Correct? Then if we take another value, that is the t is equal to t by 4, then the output voltage will be minus Vm into omega cos omega is 2 pi by t, and the t is equal to t by 4. So this will come out to be t will be cancelled. This will be a pi by 2, and the cos pi by 2 is going to be 0. So here output voltage will be 0. If we take a t is equal to t by 2, then this output voltage is minus Vm omega cos 2 pi by t into t by 2. If you calculate, then t will be cancelled. Here we have a pi, and the cos pi is cos pi will be a minus 1, and minus minus will be a plus Vm into omega. So in this way, for a different time period, if you calculate the output voltage, then your waveform will be like this. Here, the t is equal to 0, output voltage is negative. So at t is equal to 0, the output voltage is negative, and that is minus Vm into omega. Then t by 4, the output voltage is 0. So here it is 0. At t by 2, Vm omega is there. So t by 2 Vm omega, this is a Vm. Then naturally somewhere here you have a Vm omega. Correct? And in this way, if you calculate for the time 3t by 4, and then if you calculate for the time t, and if we join all these points, so this is the output waveform of the differentiator. So this is the output, and that is the cos wave. This is your the input, and that is the sine wave. Okay? So this kind of the waveform will be present if my input signal is a sine wave. Now let us see if we apply a step signal, step wave input. So what is a step wave? It is like this. Correct? This is my time t axis. This is my input voltage. Let us say the amplitude of the step wave is A. So here we have a kind of a positive wave. It is changing from 0 to A, and then it is remaining constant. So if I want to write the expression, mathematical expression for this input voltage, then we can write that the input voltage Vn is equal to A when the t is greater than or equal to 0. Okay? So when your t is 1 second, 2 seconds, 3 seconds, the output is remaining constant. And if the t is less than 0, then naturally this output is 0. Okay? So this is the expression for the step wave input. What is the output? And here we consider that the output is given by minus Rf into C1 dvi by dt, and suppose this Rf into C1 is unity, that is 1 second. So if we calculate the output voltage will be equal to minus d by dt, and the amplitude at the input is 0. A. Now A is a constant quantity, so the differentiation of A will be a 0. So ideally what should happen? When we apply the step wave input, then the output has to be 0. But if we see the waveform in the output, then it is like this. Now try to understand that for all this value of the t, for all this value of the t, output is going to be a 0. So if we draw this output, then it is like this. But at the input, what is happening? At the time t is equal to 0, the rate of change of the input voltage is very high. So dVi by dt is very, very large. Here, this input signal requires some finite time to change from 0 to A. So rate of the change of the input voltage is very large, and therefore the output voltage will be also a very large initially. So initially if we see, the rate of change of the output voltage is very large. Here it is taking some finite time to reach from 0 to A. So that here in the output also it will take some finite time to reach from a maximum value to the 0 value. Remember, so here we have a rate of change is very high, output voltage is very large, and again what is important? Important is that this is a inverting differentiator. Inverting differentiator means here we have a negative sign. The phase difference between the input and the output is 180 degree. So if here my input voltage is positive, then the output voltage will be a negative. That is due to this negative sign. So whenever the positive input voltage will be there, always the output is going, initially output is going to be a negative. And then the differentiation of this constant voltage is 0, so the output is reaching to the 0. This is known as a kind of a spike. So when we apply a step wave input, then you are getting a spike. If my step wave input is a negative, then you can have a positive spike. Okay? Now let us see that if we apply square wave input, the square wave input is like this. Correct? This is the input voltage 0, t by 2, and t is set. So the amplitude of the square wave between the time period 0 to t by 2 is plus a, and between the t by 2 t, this amplitude is minus a. So here we can write this expression that the input voltage of the square wave is plus a when the t is between 0 and t by 2. When this input voltage is minus a when this t is between a t by 2 and t. So this is a mathematical expression of a square wave. And correspondingly, if we differentiate here, so this differentiation dvi by dt, that is my output voltage. Output voltage is minus, so here we have minus d by dt, and that is the A is going to be 0. Same way, if we differentiate the output voltage during this negative, so dvi by dt, so we have equal to minus d by dt minus A, and that is also going to be a 0. So in both the case, the output will be 0. But the square wave has some finite time to reach from 0 to A. Here, it is changing from 0 to A during some finite time period. Same way, when it is changing from plus A to minus A, it is also require some finite time. So here we have a kind of a positive spike. Here you have a negative spike. Now this is a inverting differentiator. So output is going to be a inverted, and it is going to produce a kind of a spike. So if we see this waveform, here, this is my T, and let us say this is the output voltage. We have a 0. Somewhere the time period T by 2, here the time period T is there. Correct? Now, if you look at this waveform, then during this time, we have a positive spike. Now we have a inverting differentiator, so the negative sign is there. So initially you have a large negative output voltage. Remember, this is a large negative output voltage. Some negative voltage that you can calculate what is the negative output voltage. So this is nothing but it is kind of a step wave input. So in a step wave input, output will be a spike. So here we have a positive rise, so output is going to be negative, and then this output is changed in this way, and this voltage become a 0 because the differentiation of the input voltage for all these constant value, it is 0. So here it is going to be 0. Then if you see that during this time period, at the time period T by 2, the output voltage, the input voltage is changing from a plus A to minus A. Means the negative is there. So naturally, in a inverting differentiator, the output will be a positive, and that will be a larger one. Like this. And then this output voltage, here the differentiation of this output voltage is 0. So it is going to decrease in this way and become a 0. Again, if you see at the time t, the output voltage is changing from minus A to plus A, means we have a positive rise. So in a inverting differentiator, you will get a negative output, and then it is going to change in this way. So whenever we apply a kind of a square wave, then the output waveform will be, this is called a differentiating pulses. differentiating pulses. Okay? So square wave input will produce a differentiating pulses in the output of the differentiator. Now this amplitude of the differentiating pulse, that is depending on what is the time constant Rf into C1, that you can calculate. Correct? Now let us say my input voltage is a triangle wave. So if we see this waveform, correct? This is the triangle wave, time t and my input voltage Vi. Let us say the amplitude of this triangle wave is plus A. This time period is 0, this time period is t, and here you can have a time period of t by 2. Now we will see what will be the output. So for the output, we have to write the expression for the input and then we will differentiate this. So during this time period 0 to t by 2, you can see that input voltage is linearly increased with the time t. Means here if you find out the slope, you can find out the slope. Then that slope will be A. We have a positive slope. So if we write the expression for the input voltage, then this input voltage will be written as plus A into T when my signal is between 0 to T by 2. Here with the time T, this output voltage is go on increasing. You can put the T is equal to 0, the input voltage is 0, T is equal to T by 2, this voltage is going to be A. Means this is the general expression that you can say. Same way, here we can write that the Vi is equal to minus A T, where the T is between the T by 2 and the T. So, if we differentiate, remember, for this, if I will write the output voltage, then that is minus dVi by dt. So, we have minus d by dt plus at, and this output voltage comes out to be a minus A. So, that is a constant value. Again, for this, if you calculate this output voltage, minus dVi by dt is minus d by dt, we have minus at, and this will come out to be a plus A. So, whenever we have a positive slope, then the output voltage is negative, and whenever we have a negative slope, then the output voltage is going to be a positive. So, if we see this waveform, then the waveform will be like this. This is a time t. Time t axis is there, and we have this output voltage. T is equal to 0, this is my t by 2, this is a t. Now you can see during this time period 0 to t by 2, what is my output voltage? That is a minus a. So here this 0 to t by 2, sorry, this is not 0, 0 is here. So during this time period we have some negative voltage. Right? And then for the time period t by 2t we have positive voltage. So somewhere here we have kind of this positive voltage, and here there will be a change in this output voltage. Again for this time period the slope is positive, so the output voltage is going to be a negative, and then we have negative slope, so the output voltage is going to be a positive. So in this way, if R at C1 is 1, then this output voltage is going to be a plus A, and this output voltage is minus A. So when we apply a triangle wave at the input of the differentiator, then the output is going to be a positive. Now, what is the frequency response? So let us see. Okay. So in the next lecture, we will discuss the frequency response of the differentiator circuit, and then we will discuss what is the practical difficulty in this basic differentiator circuit and how we can solve this differentiator, how we can solve this problem using a practical differentiator.